The morning of December 16, 1944, arrived with darkness still thick across the landscape. At 5:31 in the morning, near the small village of Monschau on the German-Belgian border, Colonel Oscar Alfred Axelson stood before stacked ammunition crates in the gathering dawn. The officer commanding the U.S. 4006th Artillery Group gripped his field glasses and made a decision that would shatter standing orders from the highest ranks of Allied command. Through the lenses, he could make out German forces assembling in preparation for what history would eventually name the Battle of the Bulge. Operation Watch on the Rhine, Hitler's final desperate gamble in Western Europe. The 38th Cavalry Squadron, positioned along the northern flank, was about to crack under the weight of the German onslaught. His operations officer's voice cut through the tension. "Sir, German artillery preparation has commenced. The 38th is requesting immediate fire support," the man reported. Axelson turned to examine the ammunition stacked before him. These crates bore the classified marking T-98. Inside them sat proximity-fused rounds, shells that had been forbidden for use against ground targets since their creation. The technology wrapped inside these projectiles remained so classified that most American commanders had never even heard of it, let alone understood what it could do. The shells contained miniaturized radio transmitters that would trigger detonation at precisely 30 feet above the ground. When they exploded at that height, they created a devastating cone of fragments that rendered traditional foxholes worse than useless. They became death traps. Axelson gave the order, using the code designation for these weapons, the letters VT standing for variable time, chosen specifically to confuse German intelligence analysts if they somehow intercepted the communication. "Deploy the VT shells," he instructed. "We're going to need everything we have." Within 47 minutes, Axelson's unauthorized choice would introduce German combat forces to a weapon that would fundamentally reshape the final phase of World War II in Europe. The shells themselves represented something remarkable in human engineering. German scientists had declared such technology impossible. Each round embodied industrial capability that exposed the vast manufacturing gulf between American production and what German strategists had assumed about their enemy. The mathematics of killing was about to be completely rewritten. When these shells detonated at approximately 30 feet above the Earth, they unleashed fragments traveling at 3,000 feet per second, across a radius of 60 yards. No foxhole constructed in the rush of combat, no amount of earth piled overhead, no depth of entrenchment could protect soldiers from this metal rain descending from above. Military assessments ranked the proximity fuse as the third most consequential technological breakthrough of the entire war, standing behind only radar and the atomic bomb. Yet unlike those other innovations, German forces remained completely ignorant of its existence until the moment it began killing them. The device appeared simple on its surface, but represented almost impossible complexity in its execution. At its core sat a miniature radio transmitter and receiver, small enough to fit within an artillery shell's nose cone, yet tough enough to withstand acceleration forces 20,000 times more powerful than gravity itself. The system needed to detect distance from the ground and trigger detonation at the moment of maximum killing effect. Inside the fuse sat 4 vacuum tubes, not 5 as some accounts claimed, assembled into a complete radio station compressed into a space barely larger than a coffee cup, hardened to endure forces that would turn human flesh to liquid. Development had started back in 1940, consuming $1 billion in wartime money, equivalent to roughly $15 billion in modern currency. By the end of 1943, American factories were churning out 40,000 of these fuses every single day. Production would eventually climb to 70,000 daily as the war wound toward its conclusion. British scientists who first observed the technology called it the most remarkable scientific accomplishment of the entire conflict. The sheer production numbers demonstrated American industrial dominance. Between 1942 and 1945, American manufacturers built 22,733,481 proximity fuses. Of these, 21,685,157 reached combat units, while the remainder served testing purposes. Each fuse contained roughly 130 separate components, manufactured to tolerances measured in 10,000ths of an inch, assembled in sterile rooms by 110,000 workers who frequently had no idea what they were actually constructing. Engineers solved the power challenge through an elegant solution, a tiny propeller driven by wind that would only activate after the shell left the gun barrel. This miniature propeller, shielded during the violent acceleration of firing, would deploy into the rushing air stream and generate electricity to charge the capacitors powering the radio circuit, operating at frequencies between 180 and 220 MHz. The genius lay in complete inertness before firing. Once in flight, the fuse became a lethal instrument. The system remained absolutely safe to handle, impossible for enemy detection systems to locate, unreceptive to jamming attempts until the final moments of flight. The first massive deployment of proximity-fused shells against ground targets started at 6:18 in the morning on December 16, 1944, exactly 47 minutes after the German offensive began. Axelson's 406th Artillery Group unleashed fire without official authorization, responding to immediate tactical necessity. General Eisenhower would not formally request clearance until December 19th, with all restrictions officially removed by December 21st. The result struck with devastating speed and force. German soldiers charging through the pre-dawn darkness threw themselves into foxholes when American artillery opened fire, following procedures they had repeated countless times in previous battles. But something different happened this time. Instead of exploding on impact with earth, the shells detonated high above their heads. Metal fragments came screaming downward at angles that rendered foxholes worthless as shelter. The 99th Infantry Division documented the results in official reports. Concentrations of VT-fused artillery on German assembly areas near the objectives resulted in extraordinary casualties among front-line battalions within 12 minutes of the barrage starting. German medical units became overwhelmed with wounded. Attacking formations had to advance over mounting piles of their own dead to continue their assault. By December 23rd, military intelligence analysts estimated 2,000 German soldiers had been killed by proximity-fused shells during fighting around Malmedy, where artillery crews pounded SS units with devastating effect. Some attackers grew so unnerved by the onslaught that they charged directly into the incoming fire, screaming "Kamerad" in surrender. The psychological devastation exceeded even the physical destruction. To grasp how proximity fuses destroyed conventional defensive tactics, understanding the physics becomes essential. A standard high-explosive shell detonating on ground contact sends half its fragments downward into the earth, 45% outward in horizontal directions, and only 5% upward. A soldier positioned in a properly built foxhole had roughly a 90% survival rate against conventional artillery fire. Proximity fuses shattered these survival odds completely. When detonating at 30 feet altitude, 100% of fragments traveled downward or outward in an inverted cone pattern. The effective killing zone expanded from 25 yards for ground burst to 60 yards for air burst. Most critically, fragments arrived at 30 to 45-degree angles, perfectly aligned to punch into foxholes, trenches, and rifle pits. The lethal impact area jumped from 60 square feet with conventional fuses to 3,000 square feet. That represented a 50-fold increase in destructive coverage, rendering traditional field fortifications largely obsolete. This transcended simple artillery improvement. It fundamentally transformed how artillery could devastate infantry formations. The shells themselves stood as monuments to American manufacturing precision. The miniaturized components had to function after absorbing forces that would obliterate conventional electronics. The 4 vacuum tubes, a triode for oscillator and detector functions, a pentode for amplification, a thyrotron serving as the trigger switch, and occasionally a diode for rectification, were specially hardened variants that bore no resemblance to their commercial cousins. The Proximity Fuse program represented American scientific and industrial cooperation operating at peak performance. In August 1940, British scientists from the Tizard mission had shared military secrets with American counterparts, including early radar research and theoretical concepts for a proximity fuse. British researchers had proven the theory worked, but lacked the industrial infrastructure to manufacture it at scale. The National Defense Research Committee, established in June 1940, made the proximity fuse their second priority after radar development. Johns Hopkins Applied Physics Laboratory served as the development headquarters, while American manufacturers prepared their facilities for production. The obstacles seemed insurmountable. These fuses had to endure 20,000 times gravitational acceleration, function across temperatures from 50 below zero to 120 degrees Fahrenheit, spin at 30,000 revolutions per minute, and operate flawlessly after months sitting in storage ranging from humid Pacific Island conditions to frozen European depots. Section T, the classified codename for the entire Proximity Fuse initiative, employed 3,000 scientists and engineers at peak staffing. They created new polymers that wouldn't shatter under violent acceleration, miniature vacuum tubes capable of withstanding forces that would destroy ordinary electronics, and assembly procedures achieving precision measured in 10,000ths of an inch. The first successful test happened on January 29, 1942, when a proximity-fused shell brought down a target drone over Chesapeake Bay. By August 1942, the USS Cleveland carried proximity-fused anti-aircraft ammunition. The outcome proved spectacular. Japanese aircraft destruction rates climbed dramatically. The USS Helena made history on January 5, 1943, when just 4 proximity-fused shells brought down a Japanese dive bomber off Guadalcanal. Yet the military deemed the technology far too secret for ground use, where enemy forces might recover unexploded shells and study them. This restriction remained in place until the German offensive in the Ardennes threatened to fracture the Allied front, pushing field commanders like Colonel Axelson to make unauthorized choices that turned out to be absolutely correct. Before reaching ground deployment, proximity fuses had already demonstrated revolutionary capability at sea. Ocean operations eliminated capture risks, permitting unrestricted deployment against Japanese aircraft. The statistics told a compelling story. Naval vessels armed with proximity fuses required an average of 310 rounds per aircraft destroyed, compared to 1,162 rounds using conventional ammunition. By 1944, proximity-fused shells made up 25% of ammunition fired, but accounted for 51% of aircraft destroyed. During the Battle of the Philippine Sea in June 1944, proximity fuses contributed to what became known as the Great Marianas Turkey Shoot, with Japanese aircraft losses exceeding 400 machines. The weapon that would devastate German ground forces had been perfected against Japanese pilots first. The British had begun using proximity fuses against V-1 flying bombs on June 12, 1944, mere days after the Normandy landings. Anti-aircraft positions along the English coast improved their kill rate from 17% to 79% within 4 weeks. General Sir Frederick Pyle, commanding the Anti-Aircraft Command, declared it the most remarkable scientific achievement in military history. These successes made maintaining the ground use restriction increasingly difficult. Field commanders knew the technology existed and grew frustrated watching their infantry suffer casualties that proximity fuses could have prevented. The Battle of the Bulge crisis finally shattered this bureaucratic gridlock. German intelligence had actually received warnings about proximity fuses. In October 1944, General Feldmarschall Albert Kesselring's staff observed dramatic increases in Luftwaffe losses to Allied anti-aircraft fire. They found metal fragments with unusual marking patterns suggesting air detonation. A report to OKW, the Oberkommando der Wehrmacht, stated, "Evidence suggests Americans possess altitude-triggered ammunition. If adapted to ground artillery, effects on infantry would be catastrophic. Recommend immediate investigation of countermeasures." Berlin's response, found in captured documents, dismissed the warning. Medical evaluation concludes proximity detonation under battlefield conditions impossible. American anti-aircraft improvements attributed to radar direction and increased gun density. No action required. This miscalculation would cost the Wehrmacht dearly. German scientists had actually worked on proximity fuses since the early 1930s, creating 30 to 50 different designs, including acoustic fuses triggered by engine sounds, electrostatic field devices, and radio-based systems. None achieved operational status. Hitler's 1940 directive, halting all development that couldn't reach production within 6 months, effectively terminated their program. The irony cut deep. During the Battle of the Bulge, German forces captured approximately 20,000 proximity fuses, but never recognized their significance. German engineers had concluded such technology was impossible because of the massive acceleration forces involved in firing. They literally held the intelligence jackpot of the war in their hands without understanding what they possessed. 5 American corporations performed final assembly of proximity fuses. Lastly, Corporation produced 5.2 million units. Sylvania manufactured 5.7 million. RCA at 2 separate plants produced 5.9 million combined. Eastman Kodak delivered 2.4 million, and McQueen & Russ provided 2.9 million. Sylvania's facility in Ipswich, Massachusetts, represented the single highest producing location, accounting for 26% of total output. That Connecticut facility alone employed 8,000 workers and produced up to 16,500 proximity fuses daily at maximum capacity. The manufacturing precision here was absolutely extraordinary. Their quality inspectors could detect flaws so tiny they measured just 150,000th of an inch. Every single day, that massive plant demanded more electricity than entire German cities could provide. The air conditioning system never wavered, keeping temperatures stable within just 2 degrees to ensure the metal wouldn't expand or contract in ways that would destroy the tolerances they'd achieved. The quality control process was ruthless. Nearly 28% of every completed unit got rejected because it didn't meet the incredibly strict standards. For most nations, a rejection rate that high would have been devastating, completely unworkable. But American planners understood something crucial. They had such enormous production volume that they could actually afford to throw away more precision components in a single day than Germany manufactured in an entire month. The numbers simply overwhelmed the math. Sylvania dominated the entire landscape of component manufacturing. They produced 95% of all those miniature vacuum tubes that made everything work. Over 100 million tubes in total, churned out by 10,000 workers spread across 15 different plants, each one dedicated entirely to this one program. But this wasn't just Sylvania. More than 100 American companies fed into the supply chain, with over 2,000 suppliers in the mix, ranging from the smallest powder manufacturers all the way up to massive precision machine shops. And the people doing this work, the ones actually building these components, were mostly women. At Sylvania's plant in Ipswich, the numbers tell the story. Out of 10,000 workers there, 9,000 were women, many of them brought in from surrounding communities. They worked inside clean rooms where the air was filtered and controlled. Using microscopes, they verified every component placement with tolerances measured to the 2,000th of an inch. Each woman typically did just one specific task, performing it thousands and thousands of times throughout their shift, day after day. By Christmas Day in 1944, proximity fuses were actively being deployed across the entire Ardennes front. During the Battle of the Bulge, the US Army unleashed 200,000 proximity fused shells into combat. General Patton, who'd initially been skeptical about this new technology, became a complete believer after he saw what these weapons could actually do. Between December 25th and 26th, Patton's Third Army reported confirmed kills of approximately 700 German soldiers at Echternach, all taken down by proximity-fused artillery fire. His assessment became legendary. He stated bluntly that the proximity fuse had won the Battle of the Bulge for them. This was a remarkable conversion for a commander who'd always preferred tanks and mobile warfare, who'd traditionally relied on aggressive movement rather than artillery support. But the evidence was undeniable. German prisoners told their interrogators the same story over and over. They described the psychological terror of feeling completely helpless against artillery that exploded directly above their heads. Traditional military doctrine taught soldiers to seek shelter in depressions, foxholes, or trenches. Proximity fuses turned those very shelters into death traps. A captured German officer told his interrogators something that revealed the true nightmare. Your shells detonate at exactly treetop height. Always the same height. We tried everything. Deeper holes, concrete covers, spreading out across wider areas. Nothing worked. The consistency of that 30-foot detonation height, achieved through precise radio measurement, created something paradoxically more terrifying than random impacts. The enemy knew exactly what to expect, which somehow made it worse. The Hurtgen Forest, where the battle had raged since September 1944, transformed entirely when proximity fuses were authorized for use on December 18th. That dense forest, which had given German defenders concealment and protective overhead cover, became a multiplier for these new weapons' effectiveness. Tree bursts had always been deadly, but deliberately achieving them with traditional time-fused shells was incredibly difficult. Proximity fuses detonated consistently at perfect height, whether the target was open ground or thick forest canopy. The combination of steel fragments and splinters from shattered trees created an absolutely lethal storm that no field fortification could possibly withstand. The 4th Infantry Division's artillery fired 12,000 proximity-fused rounds within the first 48 hours after authorization became official. Their after-action report documented something unmistakable. Enemy casualties skyrocketed while German defensive effectiveness collapsed. Medical stations began reporting wound patterns they'd never encountered before. Deep puncture wounds concentrated on shoulders and heads, injuries clearly coming from above rather than horizontal impact. That battle became a grim testing ground for understanding exactly how proximity fuses affected combat. Artillery observers noticed something crucial. German soldiers stopped using foxholes altogether. Instead, they desperately sought overhead cover inside bunkers and buildings. This forced them into concentrated positions that became perfect targets for conventional high-explosive shells, creating a tactical nightmare with no escape route. When Operation Grenade, the Allied offensive toward the Rhine, began on February 23, 1945, the Ninth Army fired hundreds of thousands of proximity-fused shells in the opening week alone. German defensive positions they'd carefully prepared over months crumbled under airburst attack. German High Command issued increasingly desperate directives trying to counter this technology. A February 10th order demanded that all units construct foxholes measuring at least 2.5 meters deep with overhead protection made from logs with a minimum diameter of 30 centimeters, then covered with 50 centimeters of earth. By February 18th, they revised those requirements, mandating that movement through areas under artillery threat could only happen through covered trenches. Every position required concrete or steel overhead protection. These measures were physically impossible under actual combat conditions. The materials and time needed simply didn't exist. By February 26th, German command issued yet another directive that essentially admitted defeat on this front. Units would disperse to maximum distance that allowed them to maintain combat effectiveness, with no more than 2 men allowed in any single position. The Ludendorff Bridge at Remagen, captured on March 7, 1945, showed both the enormous power and the real limitations of proximity fuses. When Lieutenant Karl Timmermann requested artillery support using VT fuses to slow the German retreat across the bridge, the artillery commander refused. He cited reports that American troops were positioned too close. This documented refusal, found in official U.S. Army records, demonstrated that proximity fuses required careful tactical control to prevent friendly casualties. Germany's attempts to develop their own proximity fuses revealed the actual industrial chasm separating the two sides. Telefunken resumed research in 1944 and actually test-fired several hundred working prototypes before the war ended. But prototypes weren't the same as production models. German engineers calculated what they'd actually need: 15 new electronics factories, 50,000 specially trained workers, and manufacturing processes that didn't exist anywhere in Germany. They calculated they'd need 500 tons of refined copper monthly, 50 tons of silver for contacts, 2 million precision vacuum tubes, and 100,000 skilled workers just to approach American production rates. Even assuming those materials existed, German industry lacked the precision machine tools the job required. American factories used Swiss-made measuring instruments accurate to 1/10,000th of an inch. Germany's best machine tools, worn down from 5 years of continuous operation, achieved 1,000th-inch accuracy on their best days. The quality control requirements alone exceeded what German industry could accomplish. The deeper tragedy was that German scientists actually understood the theory perfectly. They'd actually started proximity fuse research before the Americans did. But understanding theory and actually achieving mass production were completely different problems. America hadn't just developed superior technology. They'd created an entire industrial ecosystem capable of producing it by the millions. While proximity fuses transformed ground combat in Europe, their original intended purpose, anti-aircraft defense, reached its peak effectiveness in the Pacific. By 1945, proximity-fused anti-aircraft shells were destroying Japanese aircraft with stunning efficiency. The kamikaze threat, which could have made an invasion of Japan catastrophically expensive in American lives, was substantially neutralized by VT fuses. Ships equipped with proximity fuses during the Okinawa campaign shot down 91 Japanese aircraft for every 100 attacking, compared to just 25 per 100 before proximity fuses existed. Admiral Willis Lee made the assessment directly. Proximity fuses saved 100,000 American lives in the Pacific. Every single Japanese plane shot down by VT fuses was one more that didn't crash into one of our ships. This dual application, devastating against ground forces in Europe and decisive against aircraft in the Pacific, demonstrated American industrial philosophy. Mass-produced excellence deployed everywhere. Germany struggled just to produce basic ammunition while facing an enemy that embedded sophisticated electronics into shells designed to be fired just once and destroyed. Researchers studying proximity fuse effectiveness found they were 3 to 10 times more lethal than conventional artillery when used against ground targets. Against V-1 flying bombs, destruction rates jumped from 24% all the way up to 79%. In naval anti-aircraft work, the average number of rounds needed per kill dropped from over 1,000 down to approximately 300. This 50-fold increase in lethal fragment area fundamentally changed how artillery was employed. Traditional artillery doctrine required concentrated barrages to create area coverage. Proximity fuses allowed dispersed fire to accomplish similar effects, using significantly fewer shells. This improved supply logistics, reduced barrel wear, and allowed artillery units to support more forward positions simultaneously. General Patton noted that proximity fuses let his artillery support advancing units far more effectively than ever before. Instead of lengthy preliminary bombardments, artillery could deliver shorter, more devastating concentrations that allowed infantry to push forward before the enemy could recover. This faster operational tempo directly contributed to the rapid Allied breakthroughs in 1945. However, casualty estimates require careful examination. While various numbers circulated during and after the war, documented evidence doesn't support specific large casualty claims, like 250,000 German deaths from proximity fuses alone. What is documented is their multiplication of artillery effectiveness and the psychological impact they inflicted on German forces. German recognition of proximity fuse technology arrived gradually and incompletely. Prisoner interrogations revealed most German soldiers never actually understood what was killing them. They spoke of tree bursts and air mines, but didn't grasp the systematic technological sophistication involved. German technical intelligence eventually recognized the depth of what they were facing. Captured German reports from March 1945 acknowledged that American proximity fuses represented 5 years of advancement in electronics miniaturization. Replication would require completely retooling Germany's entire electronics industry, new materials currently unavailable, and a minimum 18-month development timeline. Their recommendation was stark, impossible under current conditions. The German military's final situation report, dated May 7, 1945, stated plainly that American artillery employing proximity detonation had inflicted casualties exceeding all other weapon systems combined since December 1944. Countermeasures had proven ineffective. Their recommendation was to cease hostilities immediately to preserve whatever forces remained from annihilation by superior technology. The proximity fuse program consumed approximately 3% of all American physicists working on a single weapons project. This concentration of scientific talent, combined with industrial capacity, produced statistics that bewildered German planners. Each production line at Sylvania Corporation could assemble 500 units per hour. Workers performed individual operations in mere seconds with microscopic precision, thousands of times throughout their shift. The facilities operated around the clock, 7 days weekly. Christmas Day 1944 saw no reduction in production. While German soldiers died under proximity-fused bombardment in the Ardennes, American workers maintained maximum output without pause. The supply chain stretched across the entire nation. Copper came from Montana mines, silver drawn from treasury reserves, specialized plastics from chemical companies that hadn't existed 3 years earlier. The industrial mobilization required was as complex as the technology itself. By contrast, German ammunition production in 1945 relied heavily on forced labor, producing shells that achieved only 60% acceptable quality rates. Sabotage by those forced workers reduced effective output even further. As March 1945 approached, German artillery faced a crisis that mathematics made undeniable. Only 3 in every 10 shells leaving German gun barrels would actually work as intended. Meanwhile, the American VT fuse had achieved something remarkable: a 94% success rate, despite containing electronics so complex they seemed almost impossible to manufacture reliably. Yet this story reaches far beyond mere numbers and technical specifications. What unfolded on battlefields across Europe transcended engineering achievement. It transformed the entire experience of combat for the men facing each other across trenches and fortifications. American infantrymen felt their confidence surge as they realized their artillery support could now penetrate even the most carefully prepared German defensive positions. German soldiers, by contrast, discovered that the earth itself had lost its protective power, that centuries of military doctrine about entrenchments and dugouts suddenly meant nothing. Soldiers who survived the fighting spoke to this profound shift in their testimonies. American observers calling in fire support reported a new certainty, an assurance that their requests for artillery would actually reach targets effectively, even when those targets were sheltered. German veterans described something darker: the growing dread of hearing incoming shells, paired with the crushing realization that huddling in their foxholes offered no safety anymore. The ground that should have protected them became merely a grave waiting to happen. The wounds created presented entirely new problems for military medicine. The shells bursting overhead sent fragments downward at angles surgeons had never encountered before. Injuries presented patterns that didn't match traditional artillery casualties. German medical personnel, already overwhelmed and under-resourced, simply couldn't adapt quickly enough to these unprecedented wound characteristics. The American Medical Corps, meanwhile, had advantages that seemed almost unfair by comparison: penicillin to fight infection and blood plasma to replace what soldiers had lost. These advances had nothing to do with proximity fuses specifically, yet they multiplied the technology's devastating impact. The proximity fuse represented something larger than any single tactical advantage. It embodied American superiority in weaving together scientific discovery, industrial manufacturing capability, and military application into a coherent system. While Germany chased revolutionary wonder weapons like the V-2 rocket, pouring enormous resources into projects that yielded minimal military returns, America quietly mass-produced genuinely transformative technology and saturated the battlefield with it. Consider the contrasts through their resources spent. The German V-2 program consumed roughly $2 billion in equivalent purchasing power, yet killed approximately 9,000 people. The proximity fuse program cost approximately half that, and fundamentally altered ground combat and anti-aircraft warfare simultaneously. These numbers reveal completely different strategic philosophies at work. Germany's approach emphasized revolutionary leaps, platforms so advanced they seemed almost magical. America's strategy focused on incremental improvements manufactured at massive scale. The proximity fuse validated American organizational methods, the cooperation that flowed between Johns Hopkins scientists, the industrial manufacturers creating the devices, and the military personnel actually using them in combat. This collaborative cycle somehow compressed what should have taken years into less than 3 years from concept to mass production. German research efforts fragmented across different organizations, undermined by inter-service rivalries that prevented the kind of unified push American industry achieved. When American technical teams examined German facilities after the war ended, they discovered something fascinating. German scientists possessed genuine theoretical sophistication. They understood the principles thoroughly, but they had found no viable path to manufacturing on any meaningful scale. The German researchers grasped the fundamentals completely, yet couldn't solve the manufacturing challenges. Rheinmetall prototypes recovered in 1945 showed technical soundness, but relied upon conventional vacuum tubes that couldn't withstand the violent acceleration of a firing artillery piece. German engineers attempted multiple hardening techniques, yet never achieved the reliability that American designs had consistently demonstrated. Even had they succeeded, Germany lacked the industrial infrastructure for large-scale production. The Soviet Union received limited quantities of proximity fuses through Lend-Lease arrangements, though without any technical documentation or manufacturing specifications. Soviet engineers expended 7 years in painstaking reverse engineering of captured examples before finally producing their own working proximity fuses in 1952. Even then, their manufacturing quality remained measurably inferior to what Americans had accomplished during wartime production. This pattern of technological transfer illuminated just how complicated proximity fuse manufacturing truly was. Possessing examples proved insufficient. Successful mass production demanded industrial infrastructure that took years to develop, sophisticated quality control systems that caught microscopic defects, and manufacturing expertise accumulated through thousands of hours of hands-on experience. The proximity fuse narrative offers lessons that persist into the modern era. First, steady improvements to existing equipment often prove more decisive than revolutionary new weapons. Artillery shells remained artillery shells fundamentally, yet the proximity fuse transformed what they could accomplish completely. Second, the ability to manufacture something matters every bit as much as understanding how to design it. Germany developed jet aircraft, ballistic missiles, and advanced submarines, yet couldn't produce them in quantities that might have altered outcomes. America manufactured millions of proximity fuses, each one a sophisticated electronic device, and simply treated them as ordinary ammunition. Third, the interconnection between industrial components determines what military forces can actually accomplish. Proximity fuses demanded coordination between scientists generating novel ideas, engineers translating those ideas into practice, manufacturers bringing designs to reality, and military personnel providing feedback about what worked. American organizational culture enabled this integration naturally. German institutional rivalries prevented similar achievements. Fourth, secrecy carries both advantages and costs that must be weighed carefully. Keeping proximity fuses secret until December 1944 preserved the element of tactical surprise, but it meant additional months of Allied casualties that might have been avoided. Balancing security concerns against operational effectiveness remains an enduring challenge. The proximity fuse forces consideration of troubling moral dimensions inherent in technological warfare. The technology achieved something previously unattainable, making killing more efficient, more certain, and more precisely calculated. German soldiers crouched in foxholes had absolutely no defense against shells bursting overhead at mathematically exact heights. This wasn't combat in any meaningful traditional sense. It was mechanized slaughter. Yet this same technology hastened the war's conclusion. Every German division destroyed by proximity fused artillery represented one fewer force defending concentration camps and pursuing genocide. The weapon that killed German soldiers with such terrible efficiency also accelerated the liberation of Nazi victims from the camps. Admiral Louis Strauss, who considered proximity fuses among the developments most crucial to victory, grappled with this moral paradox. American soldiers felt similar tensions. They found relief in the technology that protected their own lives, yet felt disturbed by its capacity for devastation. Some accounts describe discovering German defensive positions where every soldier had died simultaneously, killed instantly by airburst fragments exploding overhead, a form of efficient killing that stripped away all elements of human choice or struggle. What proximity fuses ultimately represented transcended any individual weapon system. They embodied American strengths that went deeper than technology alone. They demonstrated industrial capacity capable of mass-producing sophisticated complexity, scientific talent that solved difficult problems rapidly, and organizational capability to integrate development and production seamlessly. When German infantry encountered proximity-fused artillery in December 1944, they faced something much larger than a new weapon. They confronted the physical manifestation of American industrial democracy in action, a system capable of conceiving revolutionary ideas, developing those ideas into working technology, manufacturing them in vast quantities, and deploying them globally while simultaneously conducting a worldwide war. The 30 feet separating shell detonation from ground impact represented the distance between American capability and German miscalculation. Within that brief space, measured by radio waves and calculated by miniaturized circuits, lay the gap between industrial democracy and totalitarian rigidity. Proximity fuses initiated something that extends far beyond the Second World War. They opened the modern age of smart weapons. Contemporary precision-guided munitions trace their ancestry directly to the miniaturized electronics first deployed in these fuses. The fundamental concept of embedding intelligence inside ammunition, genuinely revolutionary in 1944, is now standard military doctrine and practice globally. The manufacturing methods developed for proximity fuses shaped post-war electronics production profoundly. The rigorous quality control standards, clean room procedures demanding pristine conditions, and precision assembly techniques became foundational to the entire semiconductor industry. The women assembling proximity fuses in 1944 pioneered manufacturing methods still employed in electronics production today. The organizational lessons proved equally influential, integrating academic research, industrial production, and military application created the template for Cold War weapons development throughout the following decades. The Proximity Fuse program demonstrated that democratic societies possessed the capability to mobilize technology as effectively as authoritarian regimes, perhaps even more effectively. This account emerges from verified historical sources and documented evidence carefully examined. Production figures derive from official Bureau of Ordnance records. Technical specifications come from declassified Johns Hopkins Applied Physics Laboratory documents. Battle accounts draw from official after-action reports and established military histories. Claims lacking proper documentation have been deliberately excluded. The frequently cited casualty figures, often attributed to proximity fuses, lack credible evidence. German jamming attempts against the fuses remain unverified despite repeated claims. Certain accounts that circulate widely appear to be composite narratives combining multiple events rather than single documented occurrences. What endures following careful verification remains extraordinary nonetheless. The proximity fuse proved genuinely revolutionary, fundamentally transforming artillery from an area weapon into a precision system. Its development and successful mass production demonstrated American industrial dominance. Its battlefield employment accelerated Allied victory decisively. At 30 feet altitude, democracy defeated fascism. Not through moral idealism alone, though America possessed genuine moral advantage, but through the unglamorous excellence of mass production scaled to enormous proportions. The proximity fuse, miniaturized electronics contained within an artillery shell, embodied everything Nazi Germany had catastrophically miscalculated about American democracy. Where German leadership perceived weakness in America's diversity and pluralism, the nation discovered tremendous strength in mobilization. Jewish scientists fleeing Nazi persecution contributed their talents to proximity fuse development. Women unable to serve in combat units assembled the weapons that killed German soldiers. Somehow, democratic inefficiency produced 22 million sophisticated electronic devices, while totalitarian efficiency couldn't even manage reliable basic ammunition production. The German infantry, who confronted proximity fuses in December 1944, represented arguably the finest soldiers on the planet. They had conquered the majority of Europe, fought simultaneously on multiple fronts, and survived years of continuous combat operations. They died in their foxholes not from any lack of courage or fighting skill, but from meeting the future itself. They possessed merely 30 feet, the space between airburst and impact, to comprehend that everything they had believed regarding American weakness was fundamentally wrong. In those fractions of a second, as fragments traveled from electronic detonation to human tissue, the Third Reich's delusions confronted American reality directly. The proximity fuse killed more than German soldiers alone. It killed the mythology that martial superiority guaranteed victory, the romance surrounding defensive fortification, the notion that courage could overcome technology. Within 30 feet of altitude, measured by miniature radios employing technology seemingly impossible to create, produced in quantities seemingly impossible to achieve, America announced that future warfare would belong exclusively to nations capable of imagining innovations, engineering them successfully, and manufacturing them in extraordinary volume. Every German soldier who died beneath proximity-fused airbursts became another victim of American industrial philosophy made tangible, not victory through ideology, but through engineering excellence. Not through propaganda, but through production capability. Not through theory, but through terminal ballistics. The shells detonating 30 feet above German foxholes delivered democracy's argument against fascism through fragments, demonstrating conclusively that free societies could outmanufacture totalitarian ones, innovate more rapidly, and ultimately outfight them militarily. The proximity fuse embodied democracy's perfect weapon, simultaneously sophisticated yet mass-produced, complex yet dependable, expensive as an individual unit yet utterly expendable in aggregate. It killed with mathematical precision rather than rage. It ended battles through calculations rather than barbarism. It won wars through industrial prowess rather than cruelty. The confrontation between German infantry and proximity fuses epitomized collision between past and future directly. Defensive techniques refined across centuries of military experience became obsolete in mere moments. The protective earth that had sheltered soldiers since organized warfare provided no sanctuary any longer. The proximity fuse didn't simply kill German soldiers in isolation. It obliterated an entire military conception that had dominated thinking for generations. In December 1944, German infantry had 30 feet before proximity fuse detonations shredded their positions. In that brief distance stretched the gap between what warfare had been and what it would become. They measured their losses in meters. America measured success in megahertz. The future had arrived. It came mass-produced. It exploded precisely at 30 feet.